Hello, last time we were talking about weak acids and Kas and pKas. So let's continue with that and go to example 1812 on page 716. It says the Ka values for acetic acid and hydrofluoric acid are 1.8 times 10 to the negative fifth and 7.2 times 10 to the negative fourth, respectively. What are their pKa values? So pretty simple. Again, the P in pH, the P in POH, the P in pKw, the P in pKa means negative log. So we just take the negative log of the Ka for each of those and we get pKa. So pKa for acetic acid 4.74, pKa for hydrofluoric acid 3.14. So we see looking at the Ka values, the higher the value for Ka, the stronger the acid. It is more ionized. Conversely, the lower the pKa, the stronger the acid. Go to 1813 on the next page. Says given the following weak acids and their Ka values, arrange the acids in order of increasing acid strength and increasing pKa values. So same idea. Again, the higher the Ka, the stronger the acid. So we see in the solution there, HNO2 is the strongest, HOCl is next, HCN is the weakest, it has the lowest Ka. And of course, we see the opposite trend for pKa values. All right, some practice. Number 109 on page 740, you'll need the table that's on page 710, I believe it is. So go ahead and answer that question. Pause the video now. So once again, we'll have to look at relative strength. The stronger the acid, the more it ionizes, the more H plus ions in solution. The more H plus, the less OH minus, and the opposite is also true. And so all kinds of good important questions there. So just let me know if you have any questions about any of those. All right, next up, it doesn't say this in the notes, but we're going to talk about weak bases, and we'll use ammonia as our example. So let's first take a look at the ionization equation for ammonia. Ammonia is a weak base. In fact, many nitrogen-containing compounds are weak bases, and we'll see several examples of those. Very important, when you write the ionization equation for a weak base, you have to include water in the equation. So here is our ionization equation. And then think Bronsted-Lowry definition. Water, of course, is a liquid. And again, this is could be gas, could be aqueous. So we're talking about, maybe starting off with a solution of ammonia, then it ionizes with some more water. So typically write it like that. So let's write the base ionization constant expression. The base ionization constant is symbolized with Kb, the B for base. So again, kind of like what we did before. So we have concentration of ammonium and concentration of hydroxide on top over concentration of our base ammonia. All right, it's just like we have pKa's, there's also pKb's. Tells us something about relative strength. Once again, got a table of kb's in both the chapter 18 and in the back of the book. Same with Ka, so the higher the Kb, the stronger the base, the more it is ionized, and the opposite's also true. And of course, the lower the pKb, the stronger the base. All right, let's go to 1815 on page 720. It says calculates the hydroxide ion concentration, pH, and percent ionization for a 0.20 molar aqueous ammonia solution. So I'm not going to set it up this time because it's very similar to what we did with weak acids. So start off with the initial concentration of ammonia, 0.20 molar. And again, if you look in the book, in the ICE table, it shows 0 molar initial concentration for ammonium and about 0 for hydroxide. So once again, every aqueous solution contains both hydrogen ions and hydroxide ions. In water by itself, the concentration of hydroxide is 1 times 10 to the negative 7th. That's why they put about 0. That's really, really, really low. So for all intents and purposes, that initial concentration is 0. So the amount of NH3 will decrease as it ionizes. Amounts of ammonium and hydroxide will increase. Everything's a 1-to-1 ratio, so we have our equilibrium concentrations. Plug those into our Kb expression, that's the top of the next page, along with the Kb of ammonia, which is 1.8 times 10 to the negative fifth. Solve for X. X is, if you look in our ICE table, concentration of hydroxide, so that's the first part of the answer. Take the negative log of that, that'll give us our POH. So remember, negative log of OH minus gives us POH. If we were asked to find the pH of the solution, which we are actually, take that and subtract from 14. So it doesn't show that, but 14 minus 2.72 gives us a pH of 11.28. Make sure that your answers make sense. This is a base, so its pH should be greater than 7. So don't think that 2.72 is your answer. And then the percent that is ionized, take the amount that ionizes, which is our X value, divided by the original amount, which was 0.20 molar. Multiply that by 100, and we get 0.95% ionized. So again, going back to the setup, once again, to simplify, or you can use a quadratic formula, I guess. But we'll simplify, we'll assume X is small. So that means 0.20 minus X is really just 0.20, as it explains there in the solution. Again, we can do this if the K, Ka, or in this case Kb, is small and the initial concentration is not super duper small itself. So what is small? So kind of a 10 to the negative third, maybe 10 to the negative fourth is where we start to question if we can make that assumption. But smaller than 10 to the negative fourth, it's pretty safe to assume that X is small. So nevertheless, you want to check that assumption every time you make it. And if that assumption is not valid, then you have no choice but to use a quadratic formula to solve for X. If the assumption is valid, great, simplifies our setup, solve for X. All right, your turn. Let's go ahead and do number 53 on page 738. Take a look there because I want to show you something about how we write the equation. So in this example, it says that the substance is called benzamide. We know that this is a base because of the POH. POH is less than 7, so be careful. The pH and POH scales are opposites. So POH less than 7 is a base. So this is a base, but unless you want to look up its formula, you can just write a generic formula. So generic formula for an acid we write as HA or HX. Generic formula for a base we can write just as B. So when we write this, again, think Bronsted-Lowry definition. A Bronsted-Lowry base is a proton or hydrogen ion acceptor. So we're going to get HB plus or BH plus, either way is fine, and OH minus. All right, go ahead and finish that one and check back in just a minute when you're done. All right, so here's our setup again. We got a lot going on here, so there's a particular order. So start off with the ionization equation for the base. From that, wrote my Kb expression because we need to calculate Kb. In order to calculate Kb, we need the equilibrium concentrations of all the species in solution, not H plus, of course, but just these ones here. And then we are given the POH. So in this case, we can use that to find the OH minus concentration. So I did an anti-log of negative 2.91. That gives me 0.0012, which that goes here first. So I got my initial concentration from the problem, 0.068, initial 0, and then equilibrium concentration of hydroxide, 0.0012 molar. From there, I go here. So if we started with 0 and we have at equilibrium 0.0012 molar, concentration must have increased by 0.0012. Once I have that, I can go here, find the change in concentration of the other ion in solution, and then go here, find how much the base's concentration decreases, and then we get our equilibrium concentrations. Plug those in. We get 2.1 times 10 to the negative fifth for the KB. Question asks for the PKB, so negative log that, and we'll get our answer, which is 4.68. All right, let's take a look at a little different type of problem, 1816 on page 721. So it says a pH of household ammonia is 11.50. What is its molarity? So we're talking about the initial concentration of that solution. So take a look at the solution in the book. This time our initial concentration for NH3 is going to be X. That's what we're trying to find. We can again use the pH to find the OH minus concentration, so be careful. We want to subtract the pH from 14 to get the POH, which is 2.50, and then we can anti-log negative 2.50 to find the OH minus concentration. That's the OH minus concentration in the resulting solution, so that's our equilibrium value. So 3.2 times 10 to the negative third. So then again, that means concentration of NH4 plus and OH minus went up by that amount. NH3 concentration is going to go down by that amount. So equilibrium, we have X minus that amount. Plug those into our KB expression for ammonia. Once again, we're going to make an assumption, not that X is small this time. Remember, so we're assuming that the change in concentration is small when we're using X in our C row. And that's when we assume X is small. So here we're going to assume that 3.2 times 10 to the negative third in that bottom part of that setup is small. X minus that number is about the same as X. Make sure that makes sense. So let's solve for X. We end up with 0.57 molar. Check it out. See, 0.57 minus 3.2 times 10 to the negative third is about 0.57. So our assumption is valid. There's a problem-solving tip on the top of the next page. Talks about when we can make that assumption of X being small. Very important that you understand, because sometimes we can, sometimes we can't. And we'll see later on that we'll assume X is small in two parts of the setup, not just one. All right, next up, number 33. Let me kind of walk you through that a little bit. So we have this isotope of hydrogen called deuterium. Regular hydrogen is called protium, hydrogen 1, has 1 proton, no neutrons. Deuterium has 1 proton, 1 neutron. So we call water that has deuterium instead of protium heavy water, D2O. It's written in the equation here just like H2O, but we're substituting the H for the D. So it gives you the Kw for this reaction. Again, this is just water, and it wants you to do some interpretation of the concentrations of those ions in solution. Go ahead and pause that and see what you get. All right, take a look at the setup. So this is just like Kw, what we use with H3O plus and OH minus. We're using D3O plus and OD minus. So it tells us that the K for that reaction given to you is 1.35 times 10 to the negative 15th. And so in just that substance, the concentrations of those ions are the same. So I'm going to use X for them. So we get X squared equals our Kw. Solve for X. And then not only is that the concentrations of D3O plus and OD minus, we can use those to find the PD, which is like pH. So negative log of D3O plus concentration will give us our PD, which is 7.435. Second part of the question is D2O acidic, basic, or neutral? Take a look at the PD. You might be thinking it's basic, has a pH of greater than 7. Well, not true. Whether something is acidic, basic, or neutral depends on the concentrations of H plus and OH minus, or in this case, D3O plus and OD minus. They are the same, which tells us that this is neutral. Well, why is the PD or pH greater than 7? Well, look at the Kw. So perhaps, again, thinking about Kw, Kw is constant at a particular temperature. So we say that 7 represents a neutral solution if that solution's at 25 degrees Celsius. If it's not at 25 degrees Celsius, Kw is going to have a different value than 1 times 10 to the negative 14th. And your pH will be something other than 7. So kind of the same thing that's going on here. All right, number 57 on page 738. This actually is the same as example 1815. I don't want to redo the same whole thing. So instead of using 0.20 molar, let's use I don't know, what do you want to use? 0.40? Let's go 0.40 molar for the NH3 concentration. So very similar to the example problem 1815. So I'll let you set this up. Use 0.40, not 20 for the initial concentration of the ammonia, and the answer all parts of the question. So we want H plus concentration, OH minus, pH, POH, and percent ionization. The KB again for ammonia can be found in the book. Go ahead and pause the video and work on that now. Once again, we got a lot of stuff going on here. So start off with our ionization equation, then our KB expression, and then set up our ice table, 0.40, initial concentration, 0, 0. This is going to go down by X. Those are going to go up by X. We end up with our equilibrium concentrations, which will then plug into our equilibrium expression. So notice I took them straight from the ice table, plugged them into the equilibrium expression. And then let's simplify. So we'll assume X is small. You got to write that. And then simplify. Solve for X. We get 2.7 times 10 to the negative third. So be careful. X is our hydroxide ion concentration. So now I'm over here with our answers. Take the negative log of that to get the POH. Subtract that from 14 to get the pH. Anti-log of negative 11.43 to get the H plus concentration, and then take our X value, 2.7 times 10 to the negative third, divided by our initial concentration, 0.40 molar, times 100 to get the percent ionization, 0.68% ionized. Make sure to check your assumption of X being small, so I plugged it in here. 0.40 minus X gives us a rounded value of 0.40. So that is all good. All right, next up we have, let's see what we have next. Oh, we're frozen. There we go. We got polyprotic acids. So far everything we've been working with are monoprotic acids. And so polyprotic acids, if you recall, are acids that furnish 2 or more hydronium ions or hydrogen ions per molecule. So some common examples are sulfuric acid, H2SO4, sulfurous acid, H2SO3, phosphoric acid, H3PO4, carbonic acid, H2CO3. Those are all polyprotic acids. So something that is really, really, really important is that you have successive ionizations. For example, H2SO3 will ionize to produce HSO3 minus and H plus in solution. Well, that HSO3 minus can also ionize to make more H plus and SO3 minus 2 ions. What's really, really, really important is that each successive Ka, so the first one is called Ka1, the second one Ka2, the third one, if it's triprotic, is Ka3, is smaller, significantly smaller, by 10 to the 4th to 10 to the 6th, meaning that, for example, HSO3 minus is a much, 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 much weaker acid than H2SO3. Again, in the back of the book, you can see in the appendix that the polyprotic acids have different Kas, Ka1, Ka2, Ka3, like I mentioned, so use that table. Let's take a look at an example on how to do calculations involving polyprotic acids. All right, this is a good one. Read along, please. Calculate the concentrations of all species present in 0.100 molar phosphoric acid. Now, phosphoric acid undergoes 3 ionizations. So let me show you those equations. All right, so first one involves formation of H plus and H2PO4 minus 1 ions. Ka1 for that ionization is in the back of your book. The H2PO4 negative can also ionize, producing more H plus and HPO4 minus 2 ions. Ka2 is going to be much smaller than Ka1. Ka1 is already small to begin with. Ka2 is much smaller, and there's some significance to that, as we'll mention in just a bit. And lastly, HPO4 minus 2 can also ionize, forming more H plus ions, and this time some phosphate ions. Once again, Ka3 is much smaller than Ka2. So what species do we have in solution? We have unionized phosphoric acid. Remember, that's a weak acid, so not all of it will ionize. You have hydrogen ions. You have H2PO4 minus ions. So even though they're produced in that first ionization, if you will, and they're consumed in the second ionization, how much ionizes in that second step is not very much at all. And so we're still going to have some H2PO4 minus ions in solution. More H plus, but how much H plus is produced from that second ionization? If H2PO4 minus is a really weak acid, then you're going to produce a really small amounts of H plus in that second ionization. We'll make some HPO4 minus 2, again, a small amount, but nevertheless, it's still there. That ionizes to produce more H plus, again, much smaller than this one here. And we get some phosphate ions, and we got one more. What additional ion is in this aqueous solution of phosphoric acid? Of course, I'm talking about hydroxide. So let's take a look at the method for determining concentrations of all these substances. Start off with our Ka1. I'm at the top of page 723. Set up an ice table if you want to. Probably should. Underneath equation number 1, we end up with x squared over 0.100 minus x. And so we'll simplify. X squared over 0.100 equals a Ka1. Solve for x. And that's going to give us a concentration of H plus and H2PO4 minus, 2.4 times 10 to the negative second molar. And then the concentration of unionized acid, 7.6 times 10 to the negative second molar. Now be careful. Take a look at the next setup here. So the H2PO4 minus that was produced in the first step is our initial concentration of H2PO4 in the second ionization. So again, set up an ice table. They use Y's here, so concentration of H2PO4 minus is going to go down by Y. H plus, HPO4 minus 2 are going to go up by Y. So notice too that we have H plus ions already in solution. Initial concentration for H plus in our second ionization is not 0 because we have some already in there from the first ionization, 2.4 times 10 to the negative second. So take a look at the setup. We have 2.4 times 10 to the negative second plus Y, that's for the H plus, times Y, that's for the HPO4 minus 2, over 2.4 times 10 to the negative second minus Y. So again, look at the Ka2, 6.2 times 10 to the negative 8th. So what we're going to do here is we're going to assume that the Y, the plus Y and the minus Y don't change the value. We're going to assume those Y's are small. So take a look at the setup. We get 2.4 times 10 to the negative second times Y over 2.4 times 10 to the negative second. Those cancel. Y is 6.2 times 10 to the negative 8th, which is our concentration of HPO4 minus 2 as a result of that second ionization. I guess that's also how much more H plus is produced. But look at that compared to how much H plus was produced in the first ionization. It's much smaller. All right, one more time. We got the third ionization. So again, start off with our initial concentration of HPO4 negative 2 from the second ionization. This time they're using Z. Once again, we want to use the initial concentration of H plus that resulted from our first ionization, 2.4 times 10 to the negative second. Plug that all into the Ka3 expression. Notice Ka3 is really small. Solve for Z. This time, again, we're assuming Z is small. The plus Z and the minus Z don't change those values. And we get 9.3 times 10 to the negative 19th, which will give us our concentration of phosphates and the additional H plus, this one here, produced in solution. So take a look just below that. Add up all the H pluses from each successive ionization. 0.024 plus 6.2 times 10 to the negative 8th plus 9.3 times 10 to the negative 19th. When you add all those up, what do you notice? So the significant amount of H plus produced is what was produced in that first ionization. And so that is our concentration of H plus. Turn the page. Of course, we have to calculate also concentration of OH minus. So once we know the H plus concentration, we can use Kw to find the OH minus, which is 4.2 times 10 to the negative 13th molar. Whew, that is a lot, but make sure you understand what is going on there and make sure you can do this, because your turn. Oh, wrong page. So go ahead and do, actually, let me pause one sec. Let's first take a look at 1818 because this is a little bit different. So this is a solution of a strong polyprotic acid, being sulfuric acid. So if you look in the back of the book, the Ka1 for sulfuric acid just says very large. So that means that all of that substance ionizes. So if you take a look in the solution there, if our initial concentration of H2SO4 is 0.10 molar, then the concentration of H3O plus and HSO4 minus also 0.10 molar. And then we can set up an ICE table for the ionization of HSO4 minus. We end up with x squared over 0.10 minus x. We'll assume x is small, set that equal to Ka2. I'm not sure we can make that assumption because look at the Ka2, it's still pretty big, 1.2 times 10 to the negative second. So it looks like we cannot assume x is small because of that, so we need to use a quadratic formula to solve for x, and you get your concentrations of each of the substances in solution. So again, a little different given that the first ionization is not partial, it is complete, but everything from there forward is the same as the previous problem. All right, 61 on page 738, we'll conclude with that. Now, something I want to, let's do this, because the formula for oxalic acid is written maybe kind of a strange way, COOH2. So let's rewrite the formula for oxalic acid a different way. So remember, oxalate ion is C2O4 with a -2 charge. So what would be another way of writing the formula for oxalic acid? That would be, since it's diprotic, we have a -2 charge, so we need 2 hydrogens. H2 C2O4 instead of how it's written in the book. So go ahead and again, just like we did with these phosphoric acid, calculate the concentrations of all these species in solution. Go ahead and pause the video and work on that now. All right, here's a setup for our first ionization. So notice that Ka1 for oxalic acid is not very small, 10 to the -2, so we cannot make the assumption that x is small. So we have to get our quadratic equation and plug that into the quadratic formula. And I believe we get 0.060 for x. So that means the concentrations of H plus and HC2O4 minus are 0.060 molar. Go to our second ionization. So plug in the 0.060 molar for both the HCO2 minus 4 and H plus initial concentrations. And again, complete to the ICE table. I still use x's here. You can use y's if you want. Ka2 is pretty small, 10 to the -5th. So we'll assume x is small in this one. So simplify, we solve for x, 6.4 times 10 to the -5th. Make sure to check that assumption. 0.060 minus that is going to give you 0.060, so that's good. And so that gives us the concentration then of the oxalate ion. So 6.4 times 10 to the -5th molar for that. We have unionized, let's go to hydroxide. H plus concentration is still going to be 0.060. because 0.060 plus X is just 0.060. Use that to find the OH minus concentration, 1.7 times 10 to the negative third molar. And then going back here, unionized oxalic acid, we have 0.12 minus X. So I didn't do that one. So 0.060 gives us a concentration of 0.060 molar for the unionized oxalic acid. All right, that concludes this lesson. Next time we'll talk about hydrolysis. Thanks for watching.